Okay, all right, guys. So today we're gonna discuss about counters and shift register. Okay, so by the end of this lecture, by the way, I'm not gonna cover the whole lecture today. So mainly, I'm going to cover on the counter part first, right? Okay, but here is the lecture objectives. I mean, the idea of giving you guys the objective in the beginning of the lecture so that you know what is the goal of this lecture, right? So by the end of this lecture, you guys can measure whether you guys achieve this goal or not, right? So for example, by the end of this lecture, you guys have to understand how digital systems may be divided into data paths and control logic. I'm going to explain to you guys later what is data path and what is control logic. All this information will be used for you guys to complete your mini project, which will be given to you after you guys completed all five labs. Then we're going to start with your mini project. So that's why this is the best time for you guys to sharpen your Verilog coding skills. You know, try to spend time, try to understand the coding so that it's going to help you guys to complete your mini project. And then the second objective is to appreciate the different ways of implementing control logic. So there are many ways to implement this control logic. Then by the end of this lecture, you know, okay, there are many techniques. We can use technique A, technique B, or technique C. And then understand how shift registers and counters can be used to generate arbitrary pulse sequences. Understand the circumstances that give rise to output glitches. So we're going to discuss about what are meant by output glitches, right? So why we want to avoid output glitches, and then able to design various types of counters and timers. So these are the goals that you guys need to achieve by the end of this lecture. Okay, now we'll go into what is control logic. All right, okay, before we go into control logic, the first thing that we have to know that most of the digital systems, it can be divided into three category or three different functions. The first one is data path blocks, and then the second one is memory blocks, and then the third one is control logic blocks. All right. Okay, the first one is data path block. Right, so the data path block is where the data gonna be passing by. Okay, for an example, the ALU design that you guys are doing in lab 4, right? So let's say we have two block here, adder, and also this is your adder and this is your subtractor, and then you have two data here, A and also B, right? So both will go into both unit. It's going to go into adder and it's also going to go into S. Same goes as B. B will also go into adder and also go into the subtractor. Alright, so this is what they call is data path block. So this is data, right? This is data, the information that you guys want to process. So the information that you guys want to process will go through all of these data path block. So you're going to also have marks here, right? So the output of the adder going to go into marks where you guys going to select the marks, right? So this is your selector. Select, going to select which output that you guys going to feed out from your ALU. Either it can be adder or it can be your subtract result. Okay, that is meant what by data path blocks. Okay, and then the second one is memory blocks. Okay, so memory consists of RAM, ROM, registers, so all these things that will be used for you guys to store data. Okay, for an example, right? So we know that in a computer, right, they're going to be tremendous amount of data. So you guys need to store it somewhere because the data, you know, there's too much data that need to be processed. And then you have to have a place to stop by, right? For example, we want to go to somewhere, right? Let's say we want to go to Ipoh. I want to go to Ipoh because we want to do some shopping in Ipoh. So when we go there, because we're traveling far away, we have to stop by, right? We need to have a hotel before we go to the shopping center. So the shopping center is your data pass block. The hotel is your memory block. So they need to sit somewhere, right? To be somewhere before they go into the processing part. So that is your memory block. So these are all the basic unit that we need to have in the digital systems. So we can have a register, right? Register, and we can also have a memory. So memory can be, your RAM or ROM. So the data gonna be parked here. I mean, you can do, for example, I mean, there are 8 register, right? R0 until R8, for an example. So let's say, I mean, like you don't have this A and also you don't have B. Okay, what you have is just the marks, right? So all of the register will be passing through marks. So this is your marks. So the marks is the one that's going to output the value to S, and also there's another marks that's going to pass the value to A. Right, so you're going to choose which data that you want from the register to pass into ALU. So this is an example, right? So when your design get complicated, you need to use all these. So the expectation of mini project is you guys have to use all these block. So you need to have data pass block, you need to have memory blocks, and you also need to have the control logic blocks. Okay, when you have a massive amount of data and then you need to do the processing, I mean, who going to control this? Right? Who going to tell the circuit that, okay, now I want R0 to be added with R2, right? So who going to pick? Okay, who going to send the data to Max here? So let's say this Max 1 and this is Max 2. Who going to send the data? So that's why we need the control logic blocks. So the control logic blocks is the brain behind the digital system. So they are the one who going to send or to trigger, the select signal. So there's a control block here, for example, right? So this is your control. So the control will have, connection to the Max 1, connection to Max 2, and also connection to the ALU. Right, for example, the control, signal, the control unit want to have register 1 to be added to register 2. So they're going to send data to Max 1, okay, pick register 1, and then select data to Max 2, register 2, for example. And then they want to, the control want to add the data, then they're going to send the select signal to the Max here, which is Max 3, for an example. Then we got the addition for register 1 and register 2, and it continues. So there are going to be a lot of process. All of the process will be controlled by control unit. All right, so that is a control logic. Okay, what can we use to make the control logic? Right, for the first one, the easiest one, we can use microprocessor. Right, for an example, microprocessor, we can code it, right? So we can code it from software, and then we have a microprocessor which will change from software to the signal that can be understood by the hardware. So for example, let's say this is a calculator, right? This is a calculator, and then this is your control signal for calculator, right? So whenever you add a number on the calculator, it will store in the register, right? Then you press plus. Then you're going to tell the control signal, okay, we want to do the addition, right? So the control block here will translate the software or the push button that you select into the signal that will be sent into the hardware block. All right, so they're going to tell the ALU, okay, the user who want to execute addition, right? They already enter the first number, right, which has been stored in the first register. And then they store the second number, which is going to be add directly to the by using the adder, and then produce the result. This is example, right? So you can use microprocessor, which is I think the cheapest one. Is very flexible, right? But it's sometimes when you are designing just a basic system, right? Maybe you don't want to spend too much money, or that will cost you high by using the microprocessor. That's why we have many options to implement this control logic. So our second option is by using a synchronous state machine. Right, so we're going to cover the state machine later in our lecture. So state machine is just a state, right? So there's a state 1 and then there's a state 2. So different state will carry a different control signal. For an example, state 1 is addition. Right, so if addition, they have a fixed unit. For example, if addition, then select will be 0, 0. Right, and then the register will take from register 0, 1. And then another one will take, this is for marks 1, right? For marks 1 will take, register 1. And then for marks 2 will take from register 2. For example, this is just example, all right? Okay, so this is state, and then state 2 might be subtraction. There's also fixed signals in each state, right? So this is another method or ways that you can use for control logic. Second one is synchronous state machine. And then the third one is by using counters or shift register, right? So this is the one that we're going to cover in today's class, right? So counter and also shift register. All right, before I go into counter or shift register, do you guys have any question? Can type in chat box or can ask through mic.
Doctor.
Yep.
Counter and the shift register is the same or different?
It's different. Counter slash shift register is a different circuit. Counter is counter, shift register, shift register.
Okay, thank you.
Okay. Any more questions, guys, before I proceed? Here in this slide, the most important thing that you guys to understand the difference here. What is meant by data pass blocks, memory blocks, control logic blocks, right? And then control logic can be divided into 3 categories, right? It can be done by using microprocessor. Second, it can be done through synchronous state machine. Or the final one, it can be done through counters or shift registers. Right? Okay, hopefully you guys can follow the presentation. Okay, so now we go into synchronous counters. Okay, basically on the right hand side here is how you guys will do it in coding. So we're going to cover big things about counter, right? If you guys look into the code, I mean, it's very simple. So that's why, I mean, like, we prefer to code in Verilog because it make the designer life easy. So for example, if you want to develop a counter, so you just have a module named counter, and then it's depend on how many bits of your counter that you guys want to construct. So in this example, they're using 4 bits, 0 to 3, right? Bit 0 to bit 3, 0, 1, 2, and 3. So you have 4 bits. And then you name it as count, and then input is your clock. So input, for example, if you guys using DE2, right? If you guys look into the data sheet, they already assign a specific input for the clock. So whenever you guys want to use the clock, you guys have to connect to that specific input pin. Because I think some of you guys are still confused, what are the purpose of having the pin assignment. So, this is out of topic, right? So I just want to cover a bit more about the pin assignment. For example, right? So you guys are constructing your circuit by using Verilog in your Quartz software. So when you guys later want to transfer it into hardware, then we are dealing into the real pin. Right, so that's why when we are dealing with a hardware, we need to have the data sheet for the hardware. So the data sheet that I've shared with you guys is the DE2 board. So that is very specific. If you guys are not using DE2 board, you guys are using some other board, then you guys have to refer to that specific manual. This information is useful when you guys go, when you start working, right? All of the information that I've shared is something that is valuable for you guys later when you go into the industry. right? So I mean, if you guys understand it by now, then it make your life easier later, right? So for an example, so when you are dealing with DE2 board, specific board that I've shared the data sheet with you guys. So you guys have to check, if you guys want to connect to the 7 segment, which pin that they already connect the board on the board, right? With 7 segment with the FPGA. That's why, for example, on the board they have 8 7 segment, right? 8 7 segment. So they have a separate one. So they have 7 segment. They start it from zero. Seven. I'm not sure. I think they name it as hex, right? So 7 segment. Let's say hex zero, right? Hex 01. I'm not sure how they do it. Something like that. So this is represent. Let's see. I'm not sure. Okay. Just give you guys example here. Right. So zero, and then pin. Let's say pin. Sorry, zero. Pin 1. All right, so in 7 segment, you're gonna have 7 pins, right? 1, 2, 3, 4, 5, 6, 7. But some of it have 8 because for the dot there. Right, but okay, let's say we ignore the dot, we just have 7 here. So each of the 7 segment will have one LED. And here is one LED, another one here, another one LED, and in total you have 7 LEDs. Right, so you guys can have control on each of the LEDs. So each of the LEDs will already be connected to specific pin. For example, this pin, right? The pin 0 is this example, right? Referring to LED here. So on board is already connected to pin, let's say N17, just to give you example. So that's why you have to assign the pin because the software doesn't know which board that you guys use. You are the one who know that which board that you guys are using. So that's why you have to choose a specific pin that will connect to specific LED. Right? Okay. So then I'm hoping that you guys can have some clearance in your mind about what you guys are doing about the pin assignment. Right? So this is some things that being out of topic. Right? Okay. But yeah, I think this is gonna help you guys in your lab. All right, okay, now we go into this counter. All right, so we have 4 bits counter. Okay, remember whenever we are developing a coding within always block, right? So it has to be, the output has to be in a register form, right? So that's why we have to declare the count as register. So, okay, what happened here? Always during at the positive edge of the clock, what happened is that count will be increment by 1, right? So it start from 0, then when the, let's say this is our clock, right? Okay, so it's going to start from 0. So whenever the positive edge of the clock, they're going to check and then count will start from 0. Then after that, positive clock is going to be add by 1. No, sorry, by default, sorry. By default, before the clock start, it's already 0. So by the first clock tick, it's gonna be 1, right? So 0 plus 1 count is equal to 1, output 1. And then second clock, at the second positive edge, clock it's already 1 before 1 plus 1 is equal to 2. It's going to keep on increment until it reach 15. Okay, so let's see what happened in the clock, right? So, this is the circuitry, within the clock, what is happening inside the clock. So, how we develop a synchronous clock counter? Synchronous, whenever there's a word synchronous, that means the changes of the circuit will depend on the clock. Later, when you go into the industry, right, when they say, okay, we are using a synchronous circuit. Okay, when you heard the word synchronous, bear in mind that there are changes based on the clock. When they say, okay, we are using a synchronous circuit, okay, then okay, there's no clock involved here. So everything is just changed based on the logic, right? Okay, so synchronous counters, okay, there's a clock here being connected to the counter. And then, okay, what happened is that, okay, this is our 4-bit, right? So this is the sum block or the adder block. So as you can see here, there's a fixed input, 1. So that means this counter will be increment by 1. So what happened is start from 0, then whenever clock pass and then it pass here 0, and then it'll go here. When we go here, it's gonna add by 1, right? So the output will be 1. Output will be 1 here. And then the second clock goes high, then it's gonna output. So it's gonna output 0, 0, 0, 1. So it goes here. So 1 plus by 1, then it becomes 2. It becomes 0, 0, 1, 0. And it goes again, repeat until 15, right? But if you guys look in this circuit, what happened is that after it reach 15, it will remain 15 here because they don't reset the clock here. I mean, this is in terms of coding. But if you guys look in the state diagram here, so it changed state from 0, 1, 2, 3 until 15, then it goes into 0. So it should be when it reach 15, then the clock will reset into 0, right, and start the counter again. Okay, bear in mind that if you guys are coding by using very long, right, so it's not necessary that it's going to use, you know, the it's like a 4-bit counter exact circuit, right? So what happened is that the software will translate all your coding into basic logics, because and then they're going to optimize your logic. So the example here at the bottom is showing you guys how the optimization can be done. Okay, giving you an example here. For example, there's an input A to the AND gate here, and then there's a fixed input to the second input of the AND gate, which is 0. So in this case, we know that whenever there's an AND and then there's a 0, so the result will be always 0. So instead of having AND gate here, so they're going to simplify your circuit. So X is going to be assigned to 0. This is the example, right? The optimization that will be occurred in your in the software. It's going to be done by software without you realizing it. So that's why we don't have really care about what's happening underneath it, right? So the one that we care is the functionality here. So same goes that some of you guys ask me, right, sir, I mean, like, is my circuit correct? I mean, we don't really bother about how the circuits looks like, you know, on your design. What we bother is that, okay, is my output is correct? So that's why I'm almost in all of the lab activities, right? You guys gonna do the simulation, because that is the most important part. You guys have to go and check the simulation output waveform, whether it is correct or not. If it's correct, then okay, done, you're done. You don't have to go to circuit and check it again, wasting your time. But if there's something not right, you go and check into your coding. If your coding is fine, then you go and debug into your circuitry if there's anything wrong with your circuitry, because of this optimization algorithm. Sometimes they optimize the algorithm, and what happened is that the output doesn't really you know, come out as the one that we intend or we want it to be. All right, so that's for synchronous counter. Any question on the synchronous counter? Okay, all right, so I assume there's no question. Guys, I mean, along the way, if you guys have question, please just stop me and then I'm gonna answer you guys. So I think that's a better way of doing it, right? Okay, now synchronous counters with synchronous reset. So what happened is that, you know, sometime, so we want a clock, you know, a clock to have a, okay guys, so basically, I mean, there are 3 ways, right, of implementing the control. So one of the other way is by using clock. Okay, why we want to use clock? Okay, clock is a timing, right? It's a timing. For an example, why we want to use clock? For example, okay, let's say we want to have a control. Okay, by clock, okay, let's say we have a 16-bit of clock, right? So 1 until, 0, 1 until 15. Okay, so I mean, at every clock cycle, we can have a different control signal. For an example, when the clock is equal to 3, so what we want to have the control output to be. So let's say if at the counter equal to 3, let's say we want to execute the subtraction. This just want to give you example why we can use counter as the control. And when the clock or the counter is equal to 4, so we can, for example, execute addition. Alright, so this is just want to give you example, you know, how we can use counter as your control. So for an example, right, I mean, let's say your design, right, later for your mini project, you want to implement washing machine. Okay, washing machine, okay, then you have to determine, right, how long you're going to spin, and then how long you're going to dry it. Right, so this can be based on your timer. Okay, let's say you have a three mode of the load, right? I mean, I'm not sure if you guys have using the washing machine, right? You can look at the load here, right? So if it's a minimum, then it's going to show like that, right? Then medium, and then full load. Right, so each load gonna have a different settings. So when there's not too much close, right? So you don't have to spin, for example, rinse, right? I'm not sure. Just giving you example. So rinse, you might do it just for 20 cycles, right? 20 cycles. And then what else? Dry for, let's say 15 cycles. Just give you example. And then, but if it's medium load, for rinse, maybe you add it like 25 cycles. I mean, this is what cycle is. This is your clock, your counter cycle. So it's gonna execute until it reach 25. Then it's gonna stop. Then it's gonna go to the next state. For example, dry. So how long they're gonna dry? Because there's medium close, and then gonna increase to 20 cycles, right? So this is just example how you guys can use counter for your design later, right? Okay, now let's go back into synchronous counters with synchronous reset. Okay, now this is okay. Again, we have the same counter here. Okay, but what happened is that we are adding the reset here, reset button. So we can reset the counter whenever we want. Okay, let's look into the code first, right? So same, we have 4 bits register, right? Always, but we are adding the reset button here. So if reset is equal to 0, then count will be equal to 0. So if we press reset here, remember there's a logic here. So when we press 0, what happens is 0, and then we invert it, it becomes 1, right? So whenever it's we give 0, and then the reset that goes here will become 1. So when we press or if we give 0 here, right, we give 0, then the input that's gonna go here, it becomes 1. Right, so what happens is that whenever reset is equal to 0, then it will set the count value to 0. And if the reset is equal to 1, then they're going to start the counter. So that's what you see here, right? So this is the state diagram. So if reset button, reset button is equal to 0, which is in this case equal to 1, right? Because of the inversion here. So 1, then start counting. 1, 2, right? As long as it is equal to 1, 2, 3, 4. And then if you guys change the reset, I mean, if you give, when the reset is equal to 0, right, what happened is that it's going to reset the value again into 0. So at any position, right, at any position of the counter, you can reset the value. Okay, how it's being implemented into the circuit, it can be looked into like this, right? So you are adding an AND circuit here with your reset signal here, right? And then here is the sum of your output, and then whenever it is equal to 0, then it's gonna be reset here. So it's gonna be 0 because you end your sum result with the 0. So example given here, right? So this is your, oops, it's too long, the end gate. All right, so let's say this is your input, right? So this is your reset. So this is your reset, and here is your the sum, right? The sum, the counter. So for example, it becomes 0, 0, 0, 0, goes 0, 0, 0, 1. So what happened here is that they're going to end it. So let's say it's a 0 here. So within the circuit, what happened is that all the value here will be end with 0. So for example, here 1 will end with 0, it becomes 0. 0 will end with 0, becomes 0. 0 will end again with 0, becomes 0. And 0 from the reset will be end with the MSB here, it becomes 0. So that's why the output will become 0. So every time you press the reset button, it's going to reset the value into 0 again, and it's going to start the counting again. So let's say count until 5, then you press the reset button, it's gonna reset the value until 0, and you're gonna start the count again based on the clock. 1, 2, 3. So you can press the reset button whenever that you want, right? Whenever you press it, then it's gonna reset the value into 0. All right. So how's it, guys? Is it okay? You guys can follow me? Or you guys already fall asleep?
Yes, continue, sir.
Okay,
Yes,
good. All
we
right.
are here. We are here.
Okay, good. I'm sure none of you is celebrating Deepavali, right? Because if you guys are celebrating Deepavali, you guys are not gonna be here. B0 and B1 is 4. B0 and B, where's the B0 B1?
At the coding, so
Where?
at the coding, count equal to 1 for B0.
Oh, this one. B0. Oh, okay. All right. Okay, that's a good question. Right, count equal to, this is 1 bit. Right, so 1 bit. So here means that 1 bit, and then here is the value, bit 0. Right, so it is 0. So here is a 1 bit, and then it's a bit 1. You can also write like, okay, 2 bit is a binary, and this is your value. It can be 0, 1, right? It can be 1, 0. If you want to write 3 bits, okay, you write 3, it's a 3 bits. It is in binary, and it's a 0, 1, 0. Right? You can change whatever value as long as it is 3 bits. Okay. Clear that? So what happened is that here they just want to reset the value. Right? So count will be equal to 0 whenever you press the reset button. So whenever you don't press the reset button, so count will be increment by 1 bit, right? So add 1 becomes 1, and then add another 1 becomes 2 every changes of the clock. Okay, all right, so let's go to the next slide. Okay, decade counter, right? So decade counter. Okay, what is decade counter? So basically decade counter is a counter that you set, is a fixed reset value. So for an example here, right? So in the code example here, okay, same. So this is counter, division, mean 10, and then count, clock. And then we declare the output as 4 bits count, and then the input as clock. And then again, it is within the always block. So we have to declare the count as a register, just the output, right? So the count, which is going to be assigned to the output. No, or I mean anything that will be on the left side, right, that you're going to assign the value has to be in register form. All right, so always add positive edge of the clock. That means every changes during the positive edge of the clock, this is the positive edge of the clocks, you're going to update the value, or you're going to check the condition. Okay, now every positive edge, they're going to check if what is the value of the count. If the value of the count, okay, this is another way of declaring, right? 4 bits D9. Okay, what is D? D is decimal. So you declare it in decimal, but the maximum number is just 4 bits. So what's the maximum number that you can declare here for your 4 bit? Right? 2 to the power 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, right? So 2 to the power of 0, 1, 2 to the power of 2 is 2, 2 to the power of 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is equal to 8. So maximum number that you can declare here when you're using 4-bit is 8 plus 4 plus 2 plus 1, which is in this case is 15. So if you guys declare 16 here, you're going to get error because it's just 4-bit number. Right, so this is another way of declaring it. Okay, in this case, if the counter reach the value equal to 9, which is in binary, it will be equal to 1, 0, 0, 1. Then you're going to reset the count value and assign it into 0. Right, so that's why you see here. Although it has 4 bits where you can actually count until 15, 0 until 15, but now we have a fixed reset. So every time it reach 9, it's going to be reset to 0 and then start the count again. Right, so this is just example how you can manipulate the counter for your control circuit. And so for example, you have a 16 4-bit counter, but for your operation you just need 9 cycle, right? 9 count cycles. So this is what you can do. So you reset every time when it reach until 9. Okay, so count equal to 0. Else, right, if it is not equal to 9, and then you add it. Okay, let's go into example. Right? Okay, the counter start from 0. Right, so 0 and then check. So counter is not equal to 9, then this condition is not correct. Go into the second condition. Right, count is equal to 0 plus 1, it becomes 1, right? Then repeat it again. Every clock cycle, every positive clock cycle, repeat the process again, check, right? It's not equal to 9, then add it again. So 1 plus 1 equal to 2. Until 8 plus 1 equal to 9, then you go positive clock cycle again, check it. Okay, now count is equal to 9. Whenever count is equal to 9, then count will be set equal to 0, right? Then it's gonna start again. Okay, how we do this? Okay, we have a reset signal here. So we take the output, so let's say we use the output somewhere else, right? But we take the Q3 and we connect it to the AND gate here. And then we take Q0, we connect it to the other input of the AND gate. So this is your AND gate. AND gate. All right, so what happened is that AND gate, the output of AND will be 1 whenever Q3 and Q0 is equal to 1. So if we look into here, right? So 1001, so it's a 9 value. So this is Q0, which is your LSB, and this is your Q3, which is your MSB. So whenever both Q0 and Q3 is equal to 1, then you reset the circuit. Right, so this is how you can manipulate the counter to reset every 9 clock cycles. All right, okay. Is there any possibility that it will reset the counter although the value is not equal to 9? Right, so yes, there is, but the number will be larger than 9, which is okay for us. So this is the number that have similar output, similar value for Q0 and Q3, right? 11, you have 1011, so it's similar here. This Q0, this Q3, you have 13, 15. But it's okay because as long as the number is less than 9, there's no possibility that the output bit will becomes the Q0 will becomes 1 and Q3 will becomes 1. You can check it, right? So start from 0, 0, 0 and you do the increment 0, 0, 1, right? So this MSB not gonna be 1 up until you reach 0, 1, 1, 1, then it becomes 1, 0, 0, 0. So what's the value here? So the value here is equal to 7. Right, so anything, and this is 8, right? So it's okay, also okay. So anything less than 9 is okay. But let's say you want to reset your signal, right? You want to reset your signal when it is 13. right? So then you cannot use just Q0 and Q3, right? So you need to have additional circuitry here, right? So guess what we can do? What we can do here is just add another one. So we add Q0, Q1, Q2. Q2 is equal to 1. Q2. Alright, so this is example how we can manipulate and makes it as decade counter. So whenever we say decade counter, it's gonna have a fixed reset value. Okay, the E is already tired, that's why it's falling down. Okay guys, let's proceed. If you have any question, please let me know right in the chat box. Okay, now we are going to look into output glitches. Okay, what is meant by glitch, right? So I just Google it, right? So that you guys can understand it. So glitch means, okay, let's show the meaning here. Right, so glitch means it's a short-lived fault in the system, right? So it's a faulty in the system. So that's mean by glitch, right? So we don't want glitch. Why? Because glitch can be used for the hacker to attack. Right. So any of you guys that are into hacking stuff, right? So the things that we are looking for, the weak point of the system is glitch. So this glitch, sometimes the developer they don't realize that there's a little or small faulty in their system. So that's gonna be the point of attack, right? So that's why in design we try to avoid glitch, because glitch will make our circuit weak, and then sometimes can corrupt the result. Okay, so this is just example how we can understand what is meant by output glitches. So in this circuitry, we want to form a circuit. We want to form a circuit that the output Y here will be 1 whenever two conditions are met. The first one is when Q is equal to 0, 0, 0, 0, 0. And the second one is when the output is equal to 0, 1, 0, 0. I mean the output from the counter. Right, so let's say the output from the counter is 0, 0, 0, example here, then Y will become 0. And then when it is equal to 0, 1, 0, 0, then it will become, Y will become high here, right? So this is 4, right? Remember? 2 to the power of 0. Just want to give you guys so that you guys remember it. I mean, this is the easiest way how you want to translate the binary into decimal, right? So you can always remember this, right? So 0, 1, 2, even if you guys want to answer the exam, right? So just write this number so that you guys didn't make a mistake in the conversion between binary and also decimal. So in this case, it's 4, right? So 0, 1, 0, 0. All right, so what happened is that, okay, there are gonna be a few glitch, right? Because, I mean, what is inside here is gonna be a whole bunch of logic gates. Right, so when there's a changes in the logic blocks, the logic gates, right? Sometimes the value, is does not change simultaneously. Some value change faster than others. Some value change slower than other. Okay, example here, right? So what happened? Okay, from transition 0 to 1 is okay, right? Because 0, 1 is just from 0, 0, 0 to 0, 0, 0, 1. I mean, it does not require, I mean, it does not meet any of the condition here. Right, so it's not gonna affect the value of the Y. Okay, what happened when the value transition from 1 to 2? Right, so from 1 here to 2, 0, 0, 1, 0. Okay, what happened here is that whenever the value is changing here, you look here, right? So 1 will change to 0. Okay, if, right, let's say, I mean, there are a lot of gates, right, that gonna construct this number. So let's say 1 being processed faster than, okay, let's say, okay, Q, right? Okay, let's say this is Q 0, Q. Sorry guys, the handwriting is terrible because I'm using mouse, right? Yeah, but I think I'm getting good at it by time. So Q0, okay, let's look at the Q0, right? So at the Q0 here, this is value 0, this is value 1, and here's value 2. So the value is changing from 1 to 0. So let's say the value change faster, right? So 1 change to 0 faster than 0 change to 1. What happened is that they're gonna be at a short time, the value will be equal to 0, 0, 0. So that's why what happened is that when the value is equal to 0, 0, 0, then you trigger the Y output. So this is faulty. This is what they call as glitch, right? Because in actual, the value within here is not 0, 0, 0. It will be 0, 0, 1 changes into 0, 0, 1, 0. Right? Okay, so and then same goes after that. So there's another possibility here from 5 to 6. Why from 5 to 6? Okay, let's say 5 is equal to 0, 1. Let's do it here. 0, 1, 0, 1, which is equal to 5. Right? It changes to 6. 6 is equal to 0, 1, 1, 0. Right? So whenever, again, right? Whenever, okay, this is your Q0, Q2. Right? So whenever Q0 changes fast, then Q, hey, how come Q0, Q2? Hey, sorry guys, silly mistake. Take Q0 of the Q0, Q1, Q3, right? Okay, I'm sorry. Just make you guys confused again. So Q0, Q1, right? So Q0, Q1. Okay, if the changes in Q0 is faster, right? It changed fast, I mean it turned into 0 before Q1 changed into 1, right? So what happened is go into this condition 0, 1, 0, 0. So that's why you see another glitch here. So this is wrong. Right? We are not expecting this output. Right? So that is meant by output glitches. Okay. Okay, how we can eliminate the output glitches? So how we can eliminate the output glitches is by adding another flip-flop here. Okay, what happened is that when we add another flip-flop, we are delaying it a bit. Right, so we are delaying it by 1 count. But we get rid of the output glitch. Okay, example here, right? Okay, so whenever the output here, so we are expecting to have 1 here, right? So at 0, 0, here's 0, 0, 0, 0. So we get output 1 here. So the output 1 will go into the flip-flop, right? So whenever it's clock high, then we're gonna capture the output, then we're gonna give 1 after that. So that's why we see, I mean, like it solved the problem of glitch. But what happened is that it is what I call it, the glitch happened is a very short period of time. Right? Normally, I mean, it doesn't really realize by human eyes, but I mean, in terms of the system, of course, there's effect to the system. Right? So I mean, it's very small. I mean, it's just happening at the beginning of the signal before the signal got stable, right? So you guys remember, you guys learned about transient, right? Transient, I mean, we look at the signal is like this, it goes straight like this. But if you zoom it in, actually the signal doesn't go straight like this. It's gonna go like this. Then it's stable. Right? So this is what they call it as transient, right? Transient state. So there's a time here, right? In T. right, to change before the signal gets stable into stable state here. So what happened is that we get rid of this by having another flip-flop. So we add a flip-flop here. So by the time the output is stable, then we capture the output. So that's why you see when we capture it at the other clock cycle, right? So we capture it after the cycle after 0 here. So should be it goes here, right? But we capture the output value during clock cycle 1. Then we got the output here. Right, same goes here, but we get rid of all the glitches. Hey, I'm not sure you guys can follow me on that, right? So hopefully you guys can can cope up with my explanation. If you guys don't understand, please let me know, right? Or else I'm gonna be short sendiri. Okay, eliminating output glitches. Okay, then go next is gray code counter. Alright, gray code counter. Okay, gray code counter. So this is an alternative use account sequence where only one bit changes at a time. Okay, so we say we don't want to use this technique to eliminate the output glitches. So what we did is that we just want to have another counter. In this case here, why the output glitches occur? Because there are 2 bits, right? They need to change 2 bits here. For example, from 1 to 2, there are 2 bits that need to change to construct what they call it, decimal 2. Right? So bit Q0 and also bit Q1 need to be changed. So there are 2 bits that need to be changed that cause the output glitches. So what we can do is that we don't want to have extra additional circuit because for any reason, right? And then we want to opt for another option. Then we can use for gray counter. Right, so gray counter, if you guys look into the counter, the number of the use, all the changes just just needing 1 bit change at a time. Okay, example, right? Okay, D1. Okay, again, just right. 1 to the power of 0, 1 to the power of 1 is equal to the power of 2 is equal to 4, 8. Okay, so 0, decimal 1, right? So decimal 1 is equal to 0, 0, 0, 1. Decimal 3 is equal to 0, 0, 1, 1. So if you guys see here, from 1 to 3, they only need to change 1 bit here, which is bit Q1. And then 6 is equal to 0, 1, 1, 1. Right, then goes to 2. Right, 2 is equal to 0. D2, decimal 2 is equal to 0, 0, 1. Okay, but what is this? 2 bits happening here. Okay, wait. And then, let's check, right? So D12 is equal to 1, 1, 0, 0. What is this? Okay, alternative is where only 1 bit changes at a time. Okay, wait. Okay, now why there's a changes of 2 bits here? Okay, let's check. Okay, from here it's okay. From 1 to 3 is okay. From 3 to 6 is okay. But the problem is from 6 to 2. Oh no, okay, let's do the count here, all right? Okay, let's go through the code, all right? Okay, always count equal to d in, right? Okay, and then let's start at 0, right? Okay, for example, initial, they assign the initialize the value is equal to 0, right? So whenever the clock is high, then they're going to assign the value d in here, d in. Okay, right now d in is 0, so it's equal to 0. And then count is equal to 0, and then case count equal to 0, then they set the value. Now D in is equal to 1. Alright, so D in is equal to 1. Okay, first, let's do here. So D in, this is the first cycle, right? So D in is equal to 1. It goes up here, then as positive edge again. So D in is equal to 1. 1 is being signed to count. Count is equal to 1, right? So count equal to 1. So always when there's changes in count, case count. So check count. So when count is equal to 1, it goes into here. Right? So count is equal to 1. Now D being set into 3. The second cycle, D in being set into 3. Alright, so 3 here, then positive clock, and then go and check. So now count is being assigned to 3. Alright, so always when there's changes in count, 3, go, and then go move here, 3, right? Go 3 here, and then when it's equal to 3, then D in is equal to D2. D in is equal to D2. And then assign the value, so D in to the counter. Counter now becomes 2. Check again, okay, then it goes here. Yeah, so that's how it is. So that's why, okay, we can check here. So 1 is a 0, 0, 0, 1. 3 is equal to 0, 0, 1, 1. And then 2 is equal to 0, 0, 1, 0. Right, so okay, this one, I mean, we can ensure that all of the changes happen just involving only one bit change at a time, right? So you guys can continue, you guys can do the sequence and check. So you guys gonna realize all of the changes will just involve one bit at a time, right? So that's why, I mean, this is a gray code counter, but in the end it's gonna rotate, right? So 1, 3, 2, 6, 7, right? 5, 4. I'm not sure why there's showing a signal to 15. It's okay, just ignore it. Later I'm going to go and check it, right? Okay, so I mean, basically this is an example how they develop a counter, I mean, to avoid the glitch, right? So they just choose a number in sequence, for example, from 1 to 3 and then 3 to 2, that just involving only one bit changes at a time. Okay, so this is, I think you can go 7 to 5 or you can go 7 to 15. There's option here because 7 is equal to 0, 1, 1, 1, and 15 is equal to 1, 1, 1, 1. So just one bit change. Or you can also go to 5, which is 5 is equal to 0, 1, 0, 1. Same, right? Just one bit change at a time. So this option here. Alright, so this is an example of by using gray code counter to avoid glitches. Okay. Any question? So far so good?
Yes, sir. So far so good.
Okay. Okay, there's a question. Does this glitch have in C programming also or in circuit only? Okay, that's a good question, guys. Okay, when we talk about glitch, right? So glitch can happen both, right? It can happen in your circuitry. It can also happen in your coding, but the way it happens is different. So the way it happens in circuitry is that for example here the glitches, right, because of the circuit, because of the delay, because I mean the signal is not arriving at the same time. So that's why, I mean, there's glitches in your circuitry. But glitches in your coding is that, I mean, you don't cover, for example, you code, right? You code your coding if conditions. They say you have 3 conditions, right? But there's conditions that you don't specify, right? So, I mean, there's a part that the user can the hacker can manipulate and then goes into this blank program and then try to disturb your program. Yeah. I mean, okay, so the answer is that it can happen both in software programming and also in circuit, but the way that it happens different. Right? So circuit is involving, the circuitry itself, right? So the weakness in the circuit, but in the program is the weakness in the way you program it. That's why if you guys go into coding training, right? So there's a training that being conduct for, they call it for secure coding technique. Yeah, I've joined one when I was attached at Intel, right? So you know they teach you. I mean, this way of coding is dangerous. You don't do it this way. You have to do it another way. Yeah, so that one is the same thing. Try to avoid glitches where it's gonna open the door for the hackers to attack your system. Okay, good question. Flexible timer. Okay, this is kind of a bit complicated, but it's okay. I'll just go through it so that you guys can refer to it later, right? It's like firewall and is this like firewall and plugins? No, firewall. I mean firewall. Okay, right. Okay, that's a good question. Okay, this is your computer, right? I mean, let's say I mean let's say you are residing at Sungai Cucung, right? This is your Sungai Cucung, right? Sungai Cucung lah. You guys residing in which block? Let's say Pau lah, Pau. Okay, let's say Pau lah. Okay, this is your hostel, right? So it's your hostel, and you are connecting to the network, right? So all of the network will go from one source, which is the DMDC, right? The data management and whatever lah, DMDC, right? So all the network will go through DMDC. So you know what happened is that anybody try to attack you from outside. I mean, this is from outside, right? So it becomes, I mean, it's being done within. Then we are talking different level, right? So let's say it's being done from outside. They want to attack you, right? So it's you. You're playing your game here. I'm not sure what game is famous right now. You're happily playing your game, and somebody want to attack you, right? So attack your system or your computer. So what happens is that we put firewall here. Okay, what is firewall? Firewall is a software-based system that can trigger whenever there's a pattern of attack, right? There are many types of attacks. I mean, this is out of topic a bit, right? But as you guys have already asked it, just answering it. So there's a pattern of attack. So whenever they detect the pattern, they're gonna block it here. There's a firewall. So I mean, this firewall is quite powerful. I mean, it's gonna. I mean, it's depend on the server and what kind of firewall that you guys use. So I mean, a big company, of course, they're gonna use a super powerful firewall so that to prevent their data losses or whatsoever things that is secured in their system. So that is firewall. Okay, what is plugin? Okay, yeah, plugin is to cater for the glitches. For example, it's depend on the type of the not really plugin. It's not plugins. I mean, plugins is additional. It is software update. Right, software update is to deal with the glitches. Right, I mean, I give you example. Right, last time when I conduct lab, right, using Google Meet, I record a video. Then when I end the session, the video didn't go into my Google Drive. It goes into who's that guy name? The one that I asked in the group. Yeah, goes into his Google Drive. Right, so. And then, I mean, it shouldn't happen that way. It should mean like the system, whenever I record it, it should goes into my Google Drive. So what happened there? That is glitch. Right? And Google didn't know it. So if I contact Google and let them know, then they're going to fix it. How they're going to fix it? Of course, I mean, in this system, we're using it online, right? So they're going to fix it at the server. But for example, if you guys are using Microsoft Office, right? So if there's a glitch in your Microsoft Office, so you need to update it. Whenever you update it, they're gonna fix, right? Whatever the bug or the error in the software. And so basically those are the difference between firewalls. So it's plugins, it's not really plugins, it's update. Plugins is like, example Google Meet, right? And then here I'm using a plugin where I can update. I know when you guys join the class, I know when you guys leave the class, right? Yeah, just letting you guys know so that, I mean, I can track all of this. So then I can look at the time, what time you guys enter and what time you guys left. So that is the plugin that I add. Right? Instead of just using Google Meet, I add another plugin, additional features, to help me in taking you guys attendance. Right. So that's the plugins. Okay. By the way, it's a good question. Right. So 4:38. Okay, we still have some time. Okay, now a flexible timer. Okay, this is more technical a bit. Okay, let's erase your guys' picture first, right? Okay, so a flexible timer. So instead of having a counter that count events, we often want a counter to provide a measure of time. So we call this timer. Okay, all right. So what happened right now is that now we try to combine, right? We are combining first timer, timer, and also a counter. All right. So this is our timer, and here is our counter. All right. Oh, okay, not yet. Okay, so sorry. Okay, so sorry. I'm sorry. I mean, I'm going advanced, right? Okay, now let's talk about timer first, right? Okay, this is flexible timer. Okay, so another way of controlling is by using timer, right? Okay, so this is an example of how we can develop a timer. So instead of having counter that count events, we often want a count to provide a measure of time. So what is timer? Let's say you want to set for 1 minute time, right? So you set the timer, then you press start, it's going to count down, right? So from 1 minute, it go 59 seconds, 58 seconds up until it reach zero. Then it's going to give you some alarm, right? Beeping or whatsoever. So that is meant by timer, right? So that's why you can see it start from n. So let's say n is equal to 9, then it's going to reduce n minus 1. So 9 minus 1, 8, right? Then minus 2, minus 2, 7, right? Goes 6 until 0. Okay, and this is how the coding looks like. So n mean is your input, right? And then okay, so parameter here. Parameter is used whenever you want to use declare n bit many time, right? So instead of giving direct value, you can assign it to like a variable. So you name it n bit and then 16. So let's say whenever you want to change your design, you don't have to change at the whole part of the code. So you guys just need to change on the top part here. So that's the advantage of using parameter assignment here. Right, it's like more like into like same like C programming. Input, clock in, enable, and then n bit. So n bit here in this case we set it into 16. So 16 minus 1, which is 15. So 0 to 15 is just the same. But here we want to declare it from 0 to 1, right? So here from 0 to 16, sorry, from to make it 16 bit, so it becomes from 0 to 15. So 16 minus 1, it becomes 15. Right, I'll put tick, and then here's the code. All right, so parameter. Okay, parameter, right? So parameter is just the assignment that you give, because you can see, right? So n bit will be used multiple times here. So first being used here, and then n bit here, and then here being used second time here. Right, so in this case, right, so let's say your system is using 16 bit. So you assign the value 16 n bit here, and then you declare n bit here. Okay, what's the advantage of using this kind of declaration here? Okay, whenever you want to upgrade, let's say you want to upgrade your system. Okay, now I don't want to use 16 bit, right? I want to use 32 bits. So instead of you go here and change, right? So if you don't use n bit, then you have to declare 15 here, and then you have to declare 15 here, right? 2 times. So whenever you want to change, right, so you have to go and erase line by line. I mean, in this example, we just use it 2 times, right? But let's say you have a huge code, right? You are using it 100 times. So you don't want to go to 100 lines, find it one by one and change it, right? So we just give a name, then assign a value. So whenever you want to change the value, you just change on top of it. So instead of going and erase, okay, 15, change to 32, and then go to second line, change to 32. Instead of using that, so what you can do is that you just use the declaration here. So you just change 32 here, automatically it will be updated. Right, so it's going to be 32. 32. All right, so that's the advantage of using parameter. Okay, let's see how the timer functioning. All right, Okay, let me erase this one first. Okay. Okay, now we have 0 to 15 count, right? So always during positive age, clock in, which is your clock. Right? So this is your clock. This is your positive age of the clock. Whenever enable is equal to 1, right? So whenever enable is equal to 1, because you see here, so all of the counter only counting whenever enable is equal to 1. If enable is equal to 0, it's not going to count, right? So that's the purpose of having this code. So if only the enable is equal to 1, then go and check the condition. If count is equal to 0, okay, at the beginning, right? So count have no value, right? So at the beginning, count of course is going to be 0. If count is equal to 0, then set the tick is equal to 1. So this is your output. So count n, right? So wait, sorry. Okay, wait. Oh, sorry. Okay, I got it wrong. Wait. Okay, let's go back again. Okay, count is not equal to 0. I'm sorry. Oh yeah, yes, correct. Okay, at the beginning also again. Let's go back again. Okay, guys. Okay, now count value is equal to 0. Okay, first positive age here. Okay, first positive age here, then clock positive age, and then enable is equal to 1. Yes. Okay, then check count is equal to 0. Okay, in the beginning case, count is equal to 0. So whenever count is equal to 0, then set the tick output as 1. Okay, so tick output is equal to 1 here. It's 1. And then count is equal to n. So whatever n value, okay. So n can be 16 bit. Okay, now n is equal to 16 bits. So okay, let's say just give you an example, right? So it can be 16 bits, right? So but let's say n is equal to 4 lah, 4. So 4 is equal to 0, 1, 0, 0, right? Okay, now count is equal to 4, which is equal to 0, 1, 0, 0. Okay, at the second clock, right? Second clock, okay, enable, yes, equal to 1, check. Now, is it count is equal to 0? No. Count is already assigned equal to 4. Okay, now skip this and then go to the second condition. Else begin, okay, tick equal to 0, right? 1 bit 0. Okay, now that's why you see now tick at the second clock cycle, tick is being changes into 0. And then count is equal to count minus 1. Okay, now count is equal to count minus 1, right? Count is equal to 4. 4 minus 1 is equal to 3. Then do it again. So it's going to decrement, right? Decrement until count is equal to 0. Then it's going to start again. Right? Check the value of the n. What's the value? Assign it to n, right? So that is your timer. So by having this, you can have, for an example, right? The same goes like, I mean, let's say your washing machine example, right? Same goes. You can say, okay, I want this cycle to go up until 10 cycles, right? So you set n to 9 in decimal, right? So 9 in decimal is equal to 1001, for example, right? So and then you keep on decrement it until 0. Right? Then you set another value, for an example, right? Whatever n value that you want it to count down, right? So that is example of the timer. All right, so I think that's all for today. I'm going to continue the lecture in next week. Okay, there's a question. We assign the tick as input or output. What is tick really in Verilog? Okay, let's go look into. Okay, so the first question is, we assign the tick as input or input. Okay, let's go look into the code, right? Okay, tick. This is your, look at the diagram. That means tick is your output, right? So that's why you see in the declaration here. So we declare tick as output. All right. Okay. I think to answer this your first question, what is tick really in Verilog? Yeah, this is how tick looks like in Verilog, right? So you just declare it as output. and then we assign the value. So in this case, if count is equal to 0, we assign it to 1. If it's not equal to 0, we assign it tick equal to bit 0. Okay. All right. Any other question? Am I answering your question, Kamil? All right, good. Okay, guys. Any other question?